Welcome very much to this webinar. We'll make a presentation of the new Mako meter from RTI. And in that, I'll share a presentation with you. I'll first share my screen, and there we have the presentation. And the topic, of course, is Mako, which is our new product that we're launching, and also a little bit of feedback from RSNA in Chicago, where we were a couple of weeks ago, and where the Mako was officially launched. We had a sneak preview for distributors the week before, but that was the first big release of the Mako. So the agenda will be looking at the Mako system, look at the overview of it, give you a little bit of an insight into what the idea is and the meaning and the concept of the Mako system is. We'll look at the different components, the base unit, probes, modules, the accessories we have with it. And of course, there's also a stand available for it with a number of holders that could be interesting. Finally, how do they come? What does the packaging look like? Well, we've got a number of cases, carrying cases, that we'll also look at those different options. And last but not least, some feedback from RSNA. So the system overview. Well, the system in itself is a little bit of a new philosophy. Can say it's a revival of the Barracuda concept, where we have separate probes and the possibility to attach probes to a main unit, a base unit. But first and foremost, it's the design concept is for the most efficient X-ray meter on the market. And what do we mean by that? Well, it should be a robust system, no fuss experience, simple setup in the X-ray beam, wireless with Bluetooth, of course, and then a flexible configuration that makes it easy to use and to cover many applications that we go around. And simple setup in that it's a robust design, not only of the detector, but of the algorithms that generate the measurements. That means that we don't have to place it precisely in the X-ray beam to get a good measurement. The angular dependence is quite low. We can handle quite a wide difference in angles from the beam. So that makes it easier to set up. We don't need to be precisely in the beam. Accuracy is, of course, also important. We're aiming for the best ever practical accuracy when it comes to measurements. And the uncertainty that we've experienced and we're looking for is 1.5% of the kVp, which is unique in the market as far as we've seen. And that again is thanks to the new detector design and the algorithms that process the data received from the detector. The application range also is the best on the market, where we measure not only the traditional values like kV, dose rate, time, HVL, and total filtration, but with an additional probes, we measure the CTDI, we can measure DAP, light, beam width, and CTs, etc. So the application range is the broadest on the market. And how do we achieve this? Well, we're building on the successes of 40 years that we have been in the market, and the successes we've had with the systems like Barracuda, launched in 2000, the Piranha, the first generation, was launched in 2009, as well as Cobia and other products along the line. We also aim it to be easy to use. So with the Quick Check software and the Quick Check display software, we have the simplest to use system on the market as well. Very much appreciated from the market and the users that from which we've had very much positive feedback. Should be easy to understand how to use, intuitive to use, easy to measure, of course, to set up, and like we said, a no fuss experience. To report, of course, is becoming more and more important to have something that software that reports what you've done for traceability and for documentation. Gone are the days when you could write down the values on a piece of paper or a napkin and then do your reporting with the quick check, of course, like with Piranha, you have a very good documentation software as well. So what do we have? Well, I'm going to show you before we go there. We'll look a little bit at the system itself, look at the overview of the system. So what we do have is the base unit, which looks like this. It's the power supply, contains the battery. The battery provides 20 hours of power for typical measurement situations. And it's also the communication hub. So from here, we have a Bluetooth connectivity up to your ocean display. Or if you prefer a cabled connection, here is a dual port for both charging and for USB communication. That's a USB-C connection right there. But to make your measurements, of course, the base unit does not do any measurement at all. It's simply a power supply and a communication hub. There are three ways of connecting your probes. First one being the docking port, which is right here. And you'll see that there's a guided connection to which we can connect the probes like so. With a simple click, we get the detector or the probe in place. So that's the docking station. That's where it goes. There is also two other options to connect, and that's on either side. There is a USB-C port, one right here and one on the other side. So we can connect using a cable with a USB-C connector, like so, and connecting the probe like so for different measurement applications. So if we have a position where we need to balance it somehow, or maybe in a vascular situation, vascular application, fluoroscopy, this might be a good solution where we don't need to balance the base unit on it as well. So that again shows you a little bit about the flexibility of the connectivity in it. There can be one probe attached at any given time, and that's the limit at the moment. So here again, that's what we have. On-off switch is right here. When we switch it on, you'll see you have the LED lights go on. The green one, as on the Piranha, is the status LED. Flashing green means that it's booting, it's starting up. A solid green means that everything is okay, the system is good to go. The blue is, of course, Bluetooth. When it flashes, it's searching for a Bluetooth connection. The solid blue means that it has found a pair and it's pairing, and it's then connecting via Bluetooth. Lastly, there's also a battery charging LED that will then light up when the battery is charging. So when that goes off, the battery is full, and thus it is not charging any longer. So those are the three LEDs right there. Right, we talked about the probes. They have the same form factor in the probes. The active area is 7 by 7 millimeters, indicated by that crosshair right there. So that's the limits that indicates the size of the active area, 7 millimeters by 7 millimeters. There's also a backscatter protection collimation around it, making the total footprint 15 by 15 millimeters. That's the radiographic footprint, and we'll look at that a little bit later. So we're talking about the detector design. It's novel. Well, and it's the design is such that it's layered diodes in the detector, so that the detector has multiple layers with filters in between, dedicated special filters in between. And that then allows for the algorithms to process and to work with data and provide highest accuracy and also a very wide dynamic range. For the RF probe, which I'm holding here, the dynamic or the kV range is 35 to 155 kV. So it covers all of the radiographic and fluoroscopy and CT systems on the market today. And the interesting thing is, across that full range, the accuracy for kV is 1.5% and at 1.5% on the kVp, which is quite astonishing. We've also found, and the algorithm also provides the stability in the measurements, so that there's consecutive measurements are kept within a very narrow band, so it doesn't jump back and forth. It's reproducible and repeatable, the measurement values. So not only is it the detector stacked, the diodes, they're also segmented in each diode, which gives a number of benefits. A few of those we'll look at in a while, but it also provides the algorithms with even more ways to analyze the data and the radiation and provide a solid and high accuracy value and high accuracy measurement from this. So that's something which is quite impressive. So that's the RF probe. There is a second probe, which is the Mako probe, and as the name indicates, it's dedicated for mammography measurements. It covers the full range from 18 to 49 kV, without any fuss, without adding any filters or anything like that. Just with the detector in the beam, you get kV, dose, dose rate, HVL, and time, of course, for the mammo applications. For that full range, without adding anything or changing detectors or anything like that. Very, 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 very impressive. Although the form factor is the same, you'll see the thickness, the detector is layered, it's segmented. The filtering in between is a little bit different, so as to manage the low energies and the peculiarities of a mammo spectrum. There is a third detector. I didn't have it here, but it's a dental detector, which has a limited kV range, which is suitable for dental applications. All right, so we'll go back. I'll share my screen and presentation again where we were. We're talking about the probe design, to look a little bit more in detail on what we're up against there. Well, it's a multi-layered detector. The active area is 7 by 7 millimeters, so it's quite big, but small enough footprint, which is 15 by 15, to influence the AEC as little as possible. Now there is a balance, of course, there in fluoro applications. The size of the detector, bigger size gives a higher sensitivity, so we need to balance it to have enough sensitivity for the low dose rate fluoro, some of the low dose fluoro applications, but still provide a little footprint in the beam. So we think we've found that an optimum ratio between performance and size. We've provided a gap, a visible gap between the detector itself and the electronics in the beam, so that we can place it and have as little influence as possible of the probe in the beam. The reference level for dose is indicated. You saw it here. There's may be able to make it out, but that's a small white line. That's at 2.7 millimeters from the surface of the probe, and that's where the reference level for dose is. It's quite interesting to have it there because it gives some benefits when for instance, measuring for the AGD, where we want to look at the skin dose or the glandular dose, and we want to be as close as possible to the paddle. So with the Mamo probe, we can basically just tape it to the underside and there have a very well-defined dose reading close to the paddle, which is where the skin is, of course. Now looking at it a little bit more, we'll see that here we have a colleague who made a very nice picture of the, see if I can get the laser pointer. You see up here is on the couch is the Mako being in the beam, and the image it produces, the footprint it produces, is this. Now, of course, in a fluoro application, we would be looking at only the tip, the detector itself, and trying to position that in the beam. As you see, there's the gap is quite invisible, and the footprint of the detector itself is quite contained. So it's quite good. And this also again shows you that the design is such that the electronics itself in the hardware is resistant to direct X-ray radiation. And now, if you have some other applications where you want to have a smaller footprint, or from other setup reasons, we may disconnect here and have a cabled connection instead between the probe, which is there, and the base unit, so you can have the base unit outside the field and to have a less of an impact on the measurement. So that's what it looks like. I thought it was quite an interesting picture. Thank you, Cam. The segmented diode. Well, as we said, the diode is, or the detector is layered, multiple diodes on top of each other, filters in between. But the diodes are also segmented, which gives us not only the algorithm lots of data to input, but there are also some other benefits. In this scenario, we have a small segment in the center, which is 0.9 millimeters wide. And when can that come in handy? Well, for instance, in a panoramic dental application, the beams can be as narrow as 2 or 2.5 millimeters wide. To get a proper dose reading, well, the detector itself needs to be fully irradiated. And in that small beam, it needs then to be smaller than 2 or 2.5 millimeters. This detector here has a segment which is 0.9 millimeters big or wide, which of course then is, even for the narrowest of panoramic dental beams, will be fully irradiated. And this segmentation here has some other benefits as well. We've got the possibility to read the value, the dose hitting segment C and segment D. Now, if the beam is a little bit off to the side, say the beam is here to some extent, well, there will be an imbalance between the detector C and D. Detector C here will be getting more radiation. We can then draw the conclusion that, the beam is off a bit to the left. That means that the detector should move a little bit to the right. And if we do until we have an even balance, the same amount of radiation hitting C and segment D, we can then draw the conclusion that the beam is centered on the detector, the small detector, thereby having it fully irradiated. So that's a function that we're working on. We hope to have it included in the release and when we start shipping, which I think could be quite helpful in not only in dental but in CT applications as well. And especially if we look at what we have on the market today, which is a detector which is 4 millimeters wide. And if you have a narrow beam, 2.5 millimeters, even 3 or 3.5, that detector will not be fully irradiated. So there is a risk of a substantial risk of underestimating dose to the patient. So that's a solution that we solve in it with this segmentation of the detector. And it doesn't only underestimate the dose. Of course, you'll get an uncertainty when it comes, or an added uncertainty when it comes to HVL and KV measurements as well. All right, before we move into the holders, I'd like to talk a little bit about we talked about the base unit, we talked about the probes we have, then we also got some modules to make up that the wide application range we were talking about. The first one we're talking about is the ion chamber module, and as the name indicates, it's meant for ion chambers. The connector is LEMO, so the standard RTI CT ion chamber, for instance. The DAP chambers that we provide work well, will be managed here, as will the magnet chamber that you can buy from RTI. But also other manufacturers, if they have a LEMO connector, will be able to function with the ion chamber. And the idea is to use it. We've got the standard ion chamber, looks like this, and it's then connected to the ion chamber module, like so. And we've got an addition here, which is the dongle. And the dongle contains the calibration data for the ion chamber it's connected to. So it belongs to the ion chamber or the DAP chamber. It connects like so magnetically, and thereby will be able to transmit the data, the calibration data, and what do you call it, the type, the model, the calibration data, and serial number of the attached ion chamber that we have here. On top of that, there is also it will also read and measure temperature and pressure, air pressure. So that will then be included and compensated for directly when we add that. Connectivity, like we showed before, it goes in typically like so, and then you have a good connection like this. All right, so for CT ion chamber, DAP chamber, and the magnet chamber, that's all working this way. For those of you who have existing ion chambers, what you will need to get is that dongle. We need to know the calibration or the serial number, and we can then retrieve the calibration data from here and program the dongle and have it sent to you in there. So that was the ion chamber module. Mass module, as the name indicates, it's then for mass measurements, and those are then achieved by a cable like so, just connected to the mass module this way. These, of course, the two connectors go to the generator, So connect it to the Mako base unit, and you're good to go to measure the measure mass data. If you at the same time want to measure KV, dose rate, and those numbers, we will then be able to connect both at the same time. So we'll connect the cable to one of the USB ports, and the RF probe connects like so, and we can then have the probe in the beam, and that would be then you'd be able to read all that data at the same time, with the probe reading KV, dose rate of the exposure, and the mass module being able to read the data from the generator directly. So that's the way to do that. This is also a way to extend the reach that you have between the tube. Maybe the generator is far away in somewhere, and by using the cable to connect these, one of them, then you'd reach have a larger reach in between. There we go. And that was then the invasive mass. There will be a different cable for the mass 2. This is for invasive mass. For the mass 2 probe, there is another cable, dedicated cable for the mass 2, but the module is the very same. And there is also going to be a test point cable like we have for the Piranha, which also will connect to the mass module with its own cable. So for these, for the invasive mass, for the test point, the cables don't need to be calibrated or don't need to be sent in unless you want to, but they don't need to be calibrated. Only the mass module need to be calibrated for those applications. If you have a mass 2, that needs to come in for calibration as well, together with the mass module. Finally, we've got something we call the legacy module. And the legacy module is the interface between existing RTI probes. You might have had them, in your Piranha kits. And if you look at the port, the connector, that's a high-rose connector, which is what we have also on the Cobia Flex, for instance, and the Piranhas to connect those probes, RTI dose probes, the T20, and the functionality is similar with the legacy probe. For instance, if you want to use the CT dose profiler, we connect this one. The connector goes into, you hear the same double click as before, and we're connected. This, of course, then goes into the base unit like so, and we have the functionality for the CT dose profiler measurement like so. And this, of course, is not only for the CT dose profiler, it's for your dose probe, external dose probe, RTI dose probe, the T20, the light probe. Of course, if you have a mass 1, will also work with the legacy module, the mass 2, existing mass 2, etc. All probes that we have for the Piranha, except the chamber adapter, will not work. The improvements. That's why we have the ion chamber module, to have an improvement from the performance of the chamber adapter. So that's about it when it comes to the hardware. So then we can jump and look a little bit at what we had on the holders that come with the kit. And there's one holder, and we've got, or one stand, and we've got several holders for it. And they look like the following when you connect them. One of the holders is then to hold the probes, like so. If you for some reason need to measure at a distance or in a certain position. So it works with the RF probes, the Mamo probe, and the dental probe. Then there's the second holder, which works with the RTI dose probe and the CT ion chamber, like so. Then that may be when you have applications, again, to measure skin dose at a certain distance, or for CTDI free in air, like this, as for those applications. And then the last one, dose holder C, is for HVL filters. So you have a filter pack, and they fit into the holder nicely, and you can then do your traditional HVL measurement. If you look here at the base of the stand, you may make out there is a slot here, or for the probe, the Mamo or the RF probe, to slide in here facing up, and where the detector will align perfectly along these lines. So this line and this line, where they intersect, that's where the detector will be. So that's, if you want to do the HVL measurement, that's where you could place the probe, align this one, and then put the filters in as needed when you need to move, when you need to do the HVL measurements. Dental holder for panoramic dental, yeah, it's in place. We've improved it a bit with a better strap. So the strap is rubberized on the inside, so it creates a better friction. And then, of course, the weight of the probe is much less than the Piranha, so it's easier for it to remain in place. And the holder looks like this. When we slot the probe in, this is what it would look like in a ready state. So we have that. And then with the new functionality, of course, then we'll be able to find the beam, or find a good location for the beam easier than we had before. So it'll be interesting to see how that works in the field. Carrying cases then, yeah. Well, we've got the one I have here, which can take all bells and whistles, is the outdoor case. So it's the same form factor, same size as we have for the Piranha at present, but of course the inside is different to house the Mako and the Mako system. So that comes here. There's 2 layers. One here with most of the stuff that you need, and in the second layer there is the cables and the stand and the holders, etc., in place. So that's the outdoor case, with all bells and whistles. There will be a slightly smaller case, or a smaller case, which is a soft shell case, where you don't, if you don't need to carry the complete all bells and whistles, maybe only the bells or the whistles, but with a smaller system. So that's a soft shell case, and then there's going to be an even smaller one, which is for a very an even smaller system, for the bare minimum to carry around. So those will be the options for carrier cases when we move along. All right. So far, do we have any questions so far? We'll take some questions also towards the end, but if you have any question, raise your hand or put the question in the chat. And if there's nothing there, well, what I'd like to do is I'd like to share then a little bit about Ocean. for Mako. There's been some changes, but as you see, it's more or less the same. What we've added, what you'll see is an addition of Mako in the selection. So we had piranha, cobia, scatter probe from before, and now we've added Mako as well to this. When we start up, of course, there's going to be some differences to what we had before. For instance, now you see there's no probe connected, so the detector. So it's a little bit of a plug and play functionality in place. When we connect it like so, it should react and give us the options of functionality that we're aiming for. So in this case, it's like with the Piranha RF, radiography, fluoro, CT, and dental. And yeah, all it does is pulls up a configuration suitable for that modality. So here we've got the displays, the waveforms. I'll just put it in a beam and see if we can get some live measurement out of it. Yeah, we've got some measurements of it. So you might make out it's a little bit quicker than we had from, a little bit faster than we have from Piranha when it's response, but it's the same thing. We've got on the left displays with your different values, a waveform window. We can zoom in, magnify it. We can zoom in. We've got cursors that we can move around. So we've got some functionality like a little bit like an oscilloscope where you can measure the difference between two cursors here, 11 and 13 point. If you don't want to do the math, down here you'll see how much time there is between these cursors. And there's a horizontal cursor as well, where we can read out more exactly where we are in kV and in dose rate. So that's quite good. What you see here is that the integration frequency is 3 kilohertz. So it's not the sampling rate, it's actually the integration frequency that we see, which gives us a very, very high resolution signal in there. And of course, the log with information about the measurements that we have performed until now with the corresponding waveforms. So if we do a new quick check for fluoroscopy, it's the same thing there. We have relevant information for fluoroscopy. We have the same interest, but there is also interest in what's the number of frames and the frame rate and the dose per frame. Moving on to CT, you'll see that we've then we've been able to merge calibrations that we have in the field. So if you remember from previously, we had a setting for the GE CTs with 7-degree anode angle, 10-degree, 10.5. Aquilian had one. What we managed to do with the algorithms and the detector is to merge these informations and still make out with high accuracy, 1.5%, the kV and the dose and the HVLs. But the only thing that we're still working on is the Straton tube, which has a very special spectrum, and so we're working on getting that all into one. We're not quite there yet, but we're working on it. So for the time being, we have these two choices: the Straton tube from Siemens, and then all other tubes and CTs on the market. And if we go to dental, Yeah, there's also no more worrying about the single phase and high frequency. It's that works out just fine anyway. So that's then it for the RF probe. If we look at the Mamo probe, just clicks in like so, or we could have used the cable, of course. You'll see that there's a marked reduction in the number of calibrations that we need to choose from. And that's again thanks to the detector design and the algorithms, which has allowed us to merge some of these calibrations and the spectra to make it more manageable. But we need to state also here that for dose, which is exposure data, dose, and for HVL, the values are unaffected by the settings that we choose. The settings are more or less only for a proper KV reading. And also quite important nowadays is for documentation. So just as an example here, if we choose tungsten and the 0.7 millimeters aluminum, we'll have, of course, the accurate dose, and of course accurate HVL, because that's for all the settings. But also KV will be accurate, and it's also good for the setting to have that, so that we can document when we gathered this data, what actual setting did we use, so we have that for traceability and posterity, which we think is quite important as well. So not only for the measurement criteria, but also for documentation. And if you look here, we have then reduced them. You see, previously we have now only one tungsten and 50 micrometer rhodium, and there used to be several, and now we've reduced the number quite a lot. And that's thanks to we've managed to merge them into fewer selections that we have. Also, you will note here that it says the calibration is called tungsten and 50 micrometer rhodium, but the tolerance of the filter thickness is a little bit wider than only 50 micrometers. So we'll come up with that in the manual. What is the actual range of filter thickness for each of these calibrations? So one of these settings may cover multiple filter thicknesses. So point you to the documentation and the manuals when you're looking at that when they arrive. All right. So that's about it for the detectors, etc., and the functionality of it, as well as the Ocean software. Apart from that, the Ocean software works in the same way as we had before. We've tested it on different sites here on the market, and one of the most common comments and the feedback we get is that, well, yes, of course, it's quicker and it's more accurate than we've seen before, but it's thankful that the interface hasn't changed, because it's Ocean interface, and that makes it very easy to transition from a Piranha or a Cobia with the Ocean software in place. All right. Any questions so far? If not, then we'll do just a final summary. What we had is just a little bit of feedback from RSNA, where of course we were the week before last, and where the Mako was officially launched to a broader audience. And just some brief statistics: 25,000 external visitors plus the exhibitor staff of 17,000. So it's 40,000 plus people at RSNA this year. So it's picking up again. And we have. So it's not only an exhibition, but it's also a scientific conference for the Radiological Society of North America, where there are educational courses, scientific papers being presented. There are posters, exhibits, and also educational exhibits, apart from the exhibitors that are in the exhibition halls. There's a typo here. I see that it's not 1,120 countries, it's actually 112 countries represented in there. So it was a very big. It's a very big exhibition, one of the biggest in every year. And for us, it was quite successful. We had quite a good position. We were between Philips. There's an aisle here, but so we have Philips on one side, GE on the other side with gigantic booths. And if you look here, there's a little bit of a green hanger here on the behind that the blue Philips sign, and that's our RTI logo type. This that you see here. So it was shot from this side. So we had a very nice booth, airy booth with nice display, and even though it was airy, there was a lot of space. We were very busy, and we had lots of visitors, 3 times more than we had last year, for instance, just that, and much more than we've had the previous years. And much of that was thanks to the information and people wanting to learn more about the Mako system. And we were more than happy to share that information with them as we moved along. So the interest was good, the interest was high, the feedback was very good from the presentations, and yeah, we look forward to bringing it to the market even further as we speak.
Eric, we have a question. Yeah, we have a question from Fauci in the chat.
All right. Okay, we'll see here. Fauci. That's right. So the Mako here with, as it looks today, mass 1. That is the invasive mass for the piranha and also for cobia. With the Mako, all we need is the mass module and the mass cable. This will do the same job as the mass 1 for it. So that's we don't need the mass 1. If you like, you can still use the mass 1, but with the legacy module, which has the connector for mass 1, if you want to reuse the mass 1. For the mass module, mass 2, there will be another cable, a specific cable for the mass 2. So it will connect to the mass module. So it would look something like this. You'd have the mass module, and then the mass 2 connected like so, and you're good to go with the mass connected to the Mako. But there's a special cable for the mass 2. The module, the cables are specific here, so the module will be able to detect what type of cable is this. Is it for a mass, invasive mass, or is it for the mass 2, or is it the test point cable? So it will be able to detect that the type of cable. So that's the way the mass works. So the mass does 3 it does invasive mass, which is mass 1, but in the invasive mass into the generator, mass 2 with a clamp on, and the test point cable, and then which will double as a volt measurement as well. Will work with the mass module. You also had a question about the ion chamber. No, in the Mako system, for ion chambers, you need the ion chamber module. That's the one that works together, and that's for ion chambers. Chamber adapter will not work with Mako, not with the legacy module or anything. For ion chambers, we're shifting to the ion chamber module instead, which is a improved, further improved functionality. So that's it. Mako ion chambers, ion chamber module. So hope that was okay. Is that policy? That was okay. Very good question. Thank you, Fauzi. Since the detector, as you saw on the what do you call it? The slide of the detector design of it, the active area is 7 by 7 millimeters, so it's square. There's the detectors or the diodes are in different layers. That means that if you turn it like this, there's no change in the heel effect. The heel effect does not do anything. So we can place it any direction on the bucky. So we can place it like so. It doesn't really matter how we rotate it in a mammo, on the mammo bucky. It will give the same reading as long as we have radiation on the active area. So the active area has to be irradiated. As long as we have that, then we're okay. Then of course it's like you say here, the distance from the chest wall depends on what protocol you're following. For some protocols, it's 60 millimeters, and then of course the crosshair, the center here should be 60 millimeters or 6 centimeters from the chest wall. In some protocols, it needs to be 45 millimeters, so it depends on what protocol you're following. But that can be 45 like this, or you can have it like this, as long as the distance between the crosshair, that point, and the bucky, the chest wall, that's the distance. So it can be like like this, like this, like this. It doesn't matter how you place it. Only the distance between this crosshair here and the chest wall. That's the distance that need to be observed. So if it's 60 or 45, depends on the protocol you're following. Yeah, very good questions. Thank you, Fauzi. Any more questions? We have talking about mammo. We had some other questions also about if there is a holder for a mammo holder for the Mako probes. Not yet, because it depends on where the manufacturers want to have their reference dose measured. And so we're working with them at the moment to find out what distance does it need to be, and when that's decided, we'll be providing a holder for it. But at the moment, we don't have that information from them yet. But we're working with them at the moment. Yeah, I see you're keen to get to measure with it, Fauzi, and I can tell you it's really fun to measure. I've been to several sites to measure against a voltage divider and digital voltmeters and etc. And it's especially on the mammo side, which is tricky to measure on the different some of the beam qualities, it's been really fun. It's spot on most of the time, and sometimes we can see also that it's even better than the voltmeters when it comes to what I call it, pulsing radiation. So yes, I think you're not alone, and I think that many people would like to start measuring with Mako because it's easier, it's more precise, it's more efficient, more accurate, and has the broadest application range in the market. All right, what other questions do we have? All right, Fauzi is busy. Thank you very much, Fauzi. Yeah, of course, for measuring with on CT, we can measure. You can sit on the table. You can have it on the table, on the couch, or at the bottom of the gantry. It doesn't really matter. What matters is that we need to have that detector in place. So the distance doesn't really matter for it. But what is good, if you remember, we talked about the segmented detector. So if we put it in, if the gantry is like so, the couch is in this direction, we should put it like so, because then we have that the possibility to see the balance using the detector, the what do you call it, the segmented detector, the center detector, and to see the balance that we're actually smacking the beam for if it's a narrow beam. And yeah, putting it on the couch, we can have it connected like this. If we put it into the gantry, but I would suggest that we use the cable so that we have a better placement in the gantry for it. And again, we have a very good angular tolerance of it. So even if we're placing it a little bit like this in the beam or a little bit like that in the beam, the effect is going to be minimal when it comes to the measurements that we have there. As long as we're in this direction when the beam comes like so. So yeah, I'd do it like this in the CT with the cable connected. All right. Yeah. What else do we have? Anybody else than Fauzi? I'm sure he has more. Fauzi has more questions also. I'm sure. All right. Well, we'll be having if you're a distributor, you can go into RTI and the distributor portal and find out where and when we have trainings. We have a number of training opportunities scheduled for this first 2 quarters, quarter 1 and quarter 2, in different parts of the world. So go in or check with your area sales manager to see when those opportunities are. And we'll have them in Asia, here in Europe, and also in the Americas. So do that, and hopefully we'll see you there for some hands-on training using the Mako. Well, I think that's it for me. Thank you very much for your attention. I would like to extend the season greetings to everybody. Wish you all the best, and happy holidays, happy New Year. And if we don't see you before then, see you in 2024. Thank you very much.